Hi there, welcome back to the channel, and in today's video we will be discussing the capacitor transient response, namely the transient response of the capacitor when it charges and discharges voltage. And just to start this video off, I'll be elaborating on what I mean by transient response. To help us understand what transient response means, let's first consider this plot. In this plot, we have two key areas of interest, so let me divide that into two, and first consider the right-hand side. On the right-hand side, we have what's known as steady-state condition. In other words, when the plot has reached a value in time such that that value has now become constant and therefore no longer changes, hence steady-state condition. On the left-hand side of this plot, we have what's known as the transient response. By definition, the transient response refers to the behavior of a system or a component in response to a sudden change or disturbance in its inputs. And this change can come in many ways. It can be like an oscillatory change, like this, and therefore reach steady state at some point. So by analyzing this plot I've drawn on the bottom left, on the left hand side we have transient response, on the right hand side we have steady state, and this is what you want. You don't want it to have the other way around, because that leads to no control, such as that. So it gets worse and worse, and that would be out of our control, and we don't want that. We want these two. So in this video, the topic is a capacitor. A capacitor has two operations. We can charge a capacitor, in which the transient response would look like what I've just drawn. It would look like that. That would be the voltage, and that would be the time. And that voltage is the voltage across the capacitor as a function of time. And if we were to discharge the capacitor, again, we have time on the x-axis and the voltage across the capacitor as a function of time on the y-axis. The plot would look like this. It would exponentially decrease until it reaches steady state. So again, by analyzing these two plots for charging and discharging of a capacitor, on the right hand side of both we have steady state. On the left hand side of both we have transient response. I will now further discuss the charging and discharging of a capacitor. So to elaborate on the charging and discharging of a capacitor, let's draw an RC circuit. Here we have the voltage source, defined as Vs, and here we have point A, here we have point B, and here we have a switch that can connect to either point A or point B to form a closed circuit for operation. Here we have a resistor and a capacitor. The resistor is R, the capacitor is C, and the voltage across that capacitor, Vc of t, is considered to be the output for this circuit. So when the switch is connected to point A, the capacitor is in the charging operation. Now, I won't really go much into the derivation of how to derive these formulas. I think what's important is that you know how to apply these formulas correctly. So the voltage across the capacitor as it charges is equal to the voltage source multiplied by the bracket of 1 minus e to the power of minus t over tau. Tau is the time constant, and it's very important. The time constant, tau, is equal to the resistance multiplied by the capacitance. and the current as a function of time across the capacitor is equal to Vs over R multiplied by E to the power of minus T over tau. So what we did there is not only applied Ohm's law, but we also took out the 1 minus. That's something to consider there and to be aware of. So that's all you need to know about the charging operation. And when we connect the switch to point B, the capacitor is now in a discharging operation. So the voltage formula for this discharging operation is this time equal to the voltage source multiplied by E to the power of minus T over tau. And the current formula, IC of T, is this time equal to minus Vs over R multiplied by E to the minus T over tau. What's important here is that you consider that minus sign for the discharging of a capacitor. And if we were to plot these, here we have the voltage up here on the y-axis and time on the x-axis, it would look like this. That's charge, fully charged, and then discharge. Now, how do you know when the capacitor fully charges? What's an easy way to tell? Well, it takes 5 time constants for a capacitor to fully charge. That's like the golden rule. And likewise, it takes around 5 time constants for the capacitor to fully discharge from the initial operation of discharging. Not from 5 tau to 10 tau. It's 5 tau from when we initialize that change of operation so that the capacitor discharges. And for the current, we draw it here, just underneath. This time, the current is a bit different. It starts like this, and because of that minus sign, it drops when we initialize discharging operation, and it rises again to 0. That's what you need to consider. That's why the sign is important. And again, the same is true for the time constants. It takes about 5 tau and 5 tau again from the discharging operation initially. So I think that's a lot of what you need to know about the transient response of a capacitor. So now I believe we are ready to solve some problems to test your knowledge on this theory. So what I want you to do for this RC circuit problem is to work through each problem A, B, C and D listed beneath the circuit. I recommend that you pause the video to work on the solutions. So let's start with A. When the switch connects to point A, the time constant will be equal to 0.5 mega ohms, or in other words 0.5 times 10 to the power of 6 multiplied by 50 microfarad, in other words 50 times 10 to the power of minus 6. And this will give us an answer of 25 seconds for our time constant. Now for part B, remember that this kind of connection, when it's connected to point A, that means that this is a charging operation. So let's call back on the formula. Vc of t equal to Vs multiplied by 1 minus e minus t over tau. That's the formula we need to use for this point B problem. Question B problem, I should say. So 95% of 120 is 114. So 114 equal to 120 bracket 1 minus e minus t over 25, because we calculated tau to have a value of 25 seconds. And the objective here is to rearrange for t. So we start by dividing both sides by the voltage source, 120, 114 divided by 120 is equal to 1 minus e minus t over 25. Then the next step is to subtract 1 from both sides. So now we have 0.05 is equal to minus e to the power of minus t over tau. And the next step here is to multiply both sides by minus 1. So now we have 0.05 is equal to e to the power of minus t over tau. And now what we do now is take the natural log of both sides to get the power of the exponential term there, because we want to get t, and that's in the it's in the power area of the exponential. So ln of 0.05 is equal to minus t over 25. And now what we do next is multiply both sides by 25 and multiply both sides again by minus 1 to flip the sign. So here we have minus 25 multiplied by ln 0.05 is equal to t. Now t is equal to 74.89 seconds, which is roughly equal to 3 time constants. That's the solution for B. Now for C, at t equals 150 seconds, the switch connects to B. That means this is in discharging operation. So the new time constant is 100 kiloohms multiplied by 50 microfarad, which will give us a new time constant of 5 seconds. Now the last question here is to plot the results, and for that I will need a bit more space. So to plot this, we have time on the x-axis and Vc of t, the voltage of the capacitor as a function of time, on the y-axis. So remember, the shape for charging of a capacitor looks like this. So around the time of a full charge here is equal to 25 seconds multiplied by 5, because it takes 5 time constants to fully charge. So that what that really is, I mean, is 125 seconds. And at 150 seconds, the capacitor starts to discharge. And when that capacitor fully discharges, that value is 5 times 5 is 25, is 175 seconds. So what you really need to make clear in this plot is the times. the time values, because that's what's important here. And that's your answer for part D. So thank you very much for watching. I hope you enjoyed this video and learned something new about the transient response of capacitors. And just to let you know about the schedule for next week's video, it will be about inductors, how to calculate them in series and parallel. Thank you very much for watching once again. And don't forget to like and subscribe to support this channel.